Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 8, we will talk about fluctuations in urban water demand. The different concepts that will be covered in this lecture are on fluctuations in demand, assessment of fluctuations, and effect of fluctuations. So, when we talk about fluctuations in demand, the fluctuations in water demand, of course, the per capita water demand, this refers to the annual average daily consumption per person. So, when we talk about fluctuations, we talk about fluctuations in the annual average daily consumption per person, right. So, we have an annual consumption and how this annual consumption varies. So, there could be fluctuations during a particular month, there could be fluctuations in a particular week. So, there could be fluctuations daily and there could be fluctuations also hourly. That means, amount of water that is used varies hour to hour, day to day, week to week, and even month to month, right? Month to month, or we can also call it season to season. So, there is wide variations in this particular figure. So, even though when we determine this is the total water resource required for an urban area, or this is the total water demand for an urban area, we need to understand the variation in the demand during different, because when we overall estimate the water demand, it is like the average value, it is for the overall urban area for an annual total water demand, we will say in that terms. But at the end of the day, we have to bring it down to per day, and this value per day varies by a huge margin. So, when we design our infrastructure, when we design our pumps, when we decide on how to operate, how long to operate our pumps, we need to have absolute values or the exact values of the demand for that particular day. So, that is why we need to understand the fluctuations in demand for water demand for an urban area. So, this has not only huge implications in infrastructure design, but it has got huge implications in the operation and maintenance of the infrastructure as well. So, this depends on general habits of people. So, some of this, maybe some of the daily demand, hourly demands depends on the general habits. For example, people go to office, then they come back. So, at certain times they will use more water, and then it depends on the climatic conditions. It depends on the character of the city as an industrial, commercial, or residential. For example, in industrial city, there could be different shifts, and so you will see that before the shifts, people will use water, and then while coming back from the shifts, they will use water. So, those kind of time periods will coincide with the demand or the peak demands for that particular urban area. So, these are the different things that needs to be considered. And then we have got more water demand on Sundays and holidays, and peak hour may be around 8 am, whereas 6 am to 10 am and 4 pm to 8 pm is the peak hour on weekdays. So, during Sundays the peak hour is 8 am, and whereas for the other weekdays the peak hour is 6 am to 10 am, and then in the evening from 4 pm to 8 pm. So, this is the difference in the water demand, and minimum flow is observed usually between 2 pm to 4 am. So, these are kind of demands, this could be differences in demands could be changed, and accordingly the entire infrastructure, the entire equipments that is there in the pipeline that are used to supply water, that has to be actually adjusted. So, in this particular figure, you can see that the annual water use for New York City starting from 1898 to 1968, this has been plotted, and this on this axis there is years, and this axis this water use in millions of gallons, right. So, you can see that how water use has steadily increased over the years, and but it has not just increased in a straight line. It has also there are also variations. Sometimes it has gone up, sometimes it has gone down. This variation may be because of many other factors. So, some of these factors could be certain certain events in the city, maybe certain it may be linked with economic it could be linked with economic situation of that particular city. Maybe there is a lot of development was happening in that particular time, so there was a lot of water requirement and so on. So, then we talk about fluctuations in this per capita demand also varies from season to season, and of course, it varies even from hour to hour. But when we talk about seasonal fluctuation, we usually see in summer water demand is maximum because people use more water during bathing, cooling, lawn watering and so on. In winter the demand is less, but as I was discussing earlier, sometimes people keep their taps open and all, and that actually may lead to higher also use during winter as well. Variation may be up to 15% of the average demand of the year. So, if based on the average demand, we can see a variation of 15% during this particular. In summer it may be 15% higher, during winter it may be 15% lesser as well. So, so this is what we can see over here. This is again water supply in California, Los Angeles, California. This is again in US, water used in millions of gallons. You can see and this is the time in months, and you can see that different months the variation is different. So, the different amount of water is being used. So, that is actually being recorded over here. And again, when we talk about variation, we also see that the fluctuations occur every year and also show an increasing trend of variance. So, that means sometimes we see that the fluctuation, it is not only the fluctuations, the variance of the fluctuations also keep on increasing. So, it depends. If the demand, if the mean is higher, then and we also see a change in the variance as well. So, that means it is not during the more in future, if the demand is increasing, we see that maybe because of the different characteristics of the people or the different types of people, and we see there is the water use actually varies during different seasons, and the variation is also gradually getting increased over time. Then in this particular image, you can see that this black line is for a winter water consumption during the winter, and this red line is during this red line is for actually your this water use, and then this is the summer time. So, you can see this hourly variation is important as rate of pumping is adjusted accordingly, and this is typical, and this actually shows that during a particular day, that means during a winter, you see that this is the point where the highest water demand was there, and this is also another. There are two peaks, there is a morning peak, there is the evening peak. So, this one is a little bit lower, and during summer then you see that the peak is somewhere around over here. So, this is around 8 p.m. in the evening, you see the highest peak, right. In the morning the peak is less, in the evening when people come back they may use more water for different purposes. Maybe they will take a bath, they will do some amount of cleaning and all. So, this is where you see the maximum usage of water. So, that means the water that is to be supplied during 4 p.m. to 8 p.m. is actually much higher compared to what has to be supplied during this particular time period. So, hourly variation is important as rate of pumping is adjusted accordingly, and maximum daily consumption is usually taken as 180% of average annual consumption. So, that means maximum daily consumption, that means in a particular per day, we take that maximum day during a year is around 180% of the average consumption for that particular year. And if I take maximum hourly consumption of a particular day, it is taken around 150% of the average consumption of a particular day. So, if I take the maximum hour of the maximum day, so it is not only 180% of average, but it is also 180 into 150% of the average. So, that is 1.5 into 1.8 into annual average hourly demand, which comes to around 2.7 into annual average hourly demand. So, if the urban area has a demand for average annual demand for 200 liters per capita per day, then we divide it by 24. So, this is per hour. So, this is the average demand. So, now we multiply it by 2.7 to get the maximum hourly demand for the maximum hour of the max day. So, this is how we determine the maximum demand. So, you can see that this at some point of time during a particular year, water required would be 2.7 times more than the average. So, my network or the pipelines that will carry this water has to be designed so that they are able to carry this kind of water. Similarly, I need to have pumps so that it would be able to supply this amount of water during that particular hour, right. So, we have to design our entire system based on the peak demand. So, there is another demand which is called the coincident draft, or draft is basically the demand. So, total draft is taken as the sum of the maximum daily demand and the fired demand. So, either we take the maximum daily consumption, which is around 180% of the average, and plus we take the fired demand or the maximum hourly demand, whichever is more. So, either we take 2.7 times of the annual average hourly demand, or we take maximum daily consumption plus the fired demand, whichever is more is the coincident demand, or this is the amount of water that has to be supplied during some fighting some fire. So, this is what we need to decide. So, this is the either of coincident draft or this maximum hour max day, whichever is higher, we will design our pipe network based on that. So, Government of India has also given certain other another way to actually estimate what should be the amount of water required for particular time periods. So, they have introduced peak factors. So, when we design our network and all, we will assume we will first determine the annual average hourly demand, and then we can add a peak factor and then determine the actual flow in the networks, and we have to design our networks or we have to design our infrastructure based on that. So, up to a population of 50,000, the peak factor is 3, whereas the more we go down, the population size increases like 2 lakhs, the peak factor becomes 2, and rural standpost again it is 3. Now, why does it reduces when we have got higher population? That is because the more higher the population is, then we see that the variation actually becomes lesser. Why? Because some people would be using more, some people would be using less, so they actually cancel each other out. So, usually the peak factor becomes lesser in case of larger cities. Or similarly, when we in a pipe network, when I design a pipe network, you will see that the pipes which are near my house, there the peak factor is higher, where the pipes which are more towards the the mains, that is the main lines, there the peak factor is low, right. So, because they actually because there are so many different kinds of people at the end of that line that they cancel each other out, so that variation is less. So, this peak hour factors has to be adopted when we design any kind of water supply infrastructure. So, if I determine the maximum and the coincident draft for a city with a population of 2 lakh and a water demand of 250 LPCD, this is the average water demand of 250 LPCD, then if I find the average daily draft, this is per capita water demand per day into population. So, we find that the total requirement is 250 into 2 lakh people, this many liters per day, which comes to around 50 into 10 to the power 6 liters per day, which is around 50 million liters per day, sorry. So, this is the amount of waters that is required for this particular city that has to be supplied. So, this is the average daily draft. Now, maximum daily draft would be 180% of this. So, 180% of average daily consumption is 180 divided by 100 into 50 MLD, that is 90 MLD per day. So, that means I have to design my system to supply 90 MLD. So, if I just consider the maximum daily draft, but actually if I consider the maximum hourly draft of maximum day, it is 270% of 50 MLD. So, that comes to around 135 MLD per day, and if I convert it to hour, because it is maximum hourly draft of maximum day per hour, it comes to around 5.625 MLD per hour. So, this is the amount of water that has to be supplied per hour. This is the maximum value, and we have to design our networks based on that. Now, if you remember, I just told you earlier that we have to also consider the coincident draft. So, to understand the coincident draft, we also have to first determine the fire demand. So, we estimate the fire demand using Quichling's formula, which is 3182 into root P. This is liters per minute, and population is given in 1000. And when we give 3182 into root 200, then we get around 45,000 liters per minute, which comes to around this 45,000 into 60 into 24 liters per day, which is around 64.8 MLD per day. So, this is fire demand, even though it is estimated for a few hours, not for the entire day, but for calculation we have done it for the entire day. So, this is the fire, because it's not like the fire will burn throughout the day, but we still do this estimate, and we say that this is the maximum fire demand that is possible for this particular urban area, which is 64.8 MLD per day. Maybe there is an event where the fire has been going on throughout the day. We have seen certain cases like that. And so, coincident draft is around fire demand plus the maximum daily draft. So, that is 90 plus 64.8, which is 154.8 MLD per day, which is greater than the maximum hourly draft of maximum day, which is 135 MLD. So, we take 154.8 MLD per day as the coincident draft, which is the maximum demand that is there for a particular hour. We have to use that, and using that we will determine the size of our network, or the size of our pipeline, size of our pumps, and so on. So, this is how we will determine, this is how fluctuations actually influence the demand, or fluctuations actually influence the infrastructure, water supply infrastructure in a particular urban area. So, let us look into what is the actual effect of fluctuation on the different parts of the water supply infrastructure or equipment. So, for example, for the supply wells, that is sources of water, if it is a well, like you are drawing groundwater for an urban area, the maximum daily consumption or average daily consumption is considered. So, when we design our wells, it would be based on maximum daily consumption. So, here we are not bothered about the per hour draft or something, because we can always continuously draw water from the well and supply it in a reservoir, and this could be done at a steady rate. So, maximum daily consumption is considered, and that is all. So, again, it is not average consumption, it is maximum daily consumption has to be considered when we determine the size of our wells, because depending on the size we will be able to get certain amount of water for that, or yield of water from that particular well. Then we have for the pipelines, that is the main lines, that is source, particularly maybe from those wells, the main pipelines that brings to the service reservoir, that means from where water will be distributed, or from the treatment plants to the service reservoir, the main lines. Here again we will do it based on maximum daily consumption. Before the service reservoir, everything could be done at a steady rate, and so maximum daily consumption is good enough. Hourly consumption difference will be taken care by the service reservoir itself. So, treatment plants maximum daily draft, either we can take 1.8, that is maximum daily consumption is 1.8 times into average consumption, either we can take that, but we can take a little bit higher, because there is sometimes there is breakdown in the plants and all. So, we take a safety factor and we take around 2 times into average consumption if breakdowns are considered. So, similarly for pumps, we take around 1.8 times into average consumption, or 2 times if breakdown is considered. Now, for distribution system, service reservoir to building, so this is the pipe network which originates at the service reservoir and then goes to your building. Here we take maximum hourly draft of maximum day, or coincident draft, whichever is more. So, this is where the actual supply happens, because reservoir is where water is stored. You can store the water in a steady state, steady rate, and then you can use the water out of the reservoir at a much higher rate at certain time, other period you can use it at a lesser rate. So, actually the purpose of reservoir is to balance this particular demand, right. So, we will discuss that in later chapters. So, you can see that over here in this particular pipeline, maximum hourly draft of maximum day or coincident draft, whichever is more, that is actually taken. So, this service reservoir is basically designed to balance the fluctuation, and so the service reservoir size is fire demand for 2 hours plus emergencies, breakdowns and all, that has to be considered when we design the service reservoir. For service reservoir, we consider these variations in fluctuations, that has to be considered, plus fire demand if we have to meet the fire demand, and then emergencies. All these things has to be considered when we determine the size of the service reservoir. This we will explain in detail in a later lecture. So, in this particular image you can see this is the distribution system, this is our service reservoir over here, this is the pipeline to the distribution system, and this is our source, maybe a river, this is our intake, this is our mains, this is our main line which comes to the treatment plant. Maybe there is a pump involved over here which lifts the water into the treatment plant, and from the once the water is treated, again there is a pump involved which will lift the water into this service reservoir, and then from service reservoir it is distributed into this distribution network. And you can see that's why, that means over until this service reservoir everything could be based on the maximum daily consumption, but of course because there are mechanical system involved in the treatment units and the pumps, there we actually can go for a little bit higher 2 times, and whereas beyond the service reservoir it is based on the coincident draft, or the higher of the coincident draft or the maximum hourly draft. Based on that we will design the network. So, to conclude, the per capita demand for water varies monthly, weekly, daily and hourly, and needs to be considered in water supply infrastructure and equipment design and operation. The effect of water demand fluctuation is different for different infrastructure and equipment of water supply scheme. So, that has to be considered. And finally, the entire distribution system has to be designed considering the higher of the coincident draft or the maximum hourly draft of the maximum day. So, these are the references you can consider. Thank you.